Hi, so today we'll be doing the question 2 of homework 11 for probability and stochastic processes. Now the second question says that we're given three functions, which are these three, and we're given them in terms of v, a variable v. So that's fine, and the question says that we have to check whether this function that we're given, if we substitute instead of v a tau in it, does it represent an autocorrelation function, all of them? And if we substitute an omega in them, do they represent a power spectral density function? So for that, we basically need a few conditions before we move on to the questions, and I've written those out. So for any function to be of past spectral density, the main thing is that the value of s of omega should always be greater than 0. So it should be always positive for it to exist. And for a function to be an autocorrelation function, its Fourier transform, the Fourier transform of autocorrelation function is a past spectral density. So that should always be greater than 0. And except for that, that should be 0, but also along with that is that the autocorrelation function itself should be greater than 0. So we see that an autocorrelation function can only exist if the past spectral density exists, but that's not the same for the way opposite. So now we're gonna go ahead into the question. So the first part says that we're given a function f of the function in terms of v is e to the power minus magnitude of v. So now in the first case, we'll substitute instead of v tau, and we'll try to see if it's an autocorrelation function or not. So when we do that, we get e of minus of magnitude of tau. And when we take its Fourier transform to find out the corresponding spectral density, what we get is we use that the transformation which had e to the power minus alpha mod tau. So alpha in this case is 1 basically, so we get 2 into 1 by 1 plus omega squared. This entire term, can never go negative because it has a square in terms of omega, and the only thing that it depends on is omega. So even if you give it a negative value or 0 or anything, it'll always be positive. So this autocorrelation function can exist. Now similarly, we see about the power spectral density, e to the power minus mod of omega. Now, we know that the value of exponential, even if it is negative 1, it's going to be an exponentially dying out value. It's not going to go negative. It's going to start at 1 and then it's going to go down. But it's never even going to reach 0. It's going to die out. That's it. So it can also exist. Second part says that sine square v by v squared. So this is basically a sinc function, but it's squared of a sinc function. So the part that used to come over here, negative go like that, that's going to just pop up because it's squared now. So it'll be positive. So now first we do for the autocorrelation function, we get a sine squared tau by tau squared. So we're going to take the Fourier transform of this to check whether the corresponding power spectral density exists. To find out the transform for this, I've used Wolfram Alpha. This is an online tool. So upon entering this input equations, what we get is that the Fourier transform of this is going to look something like a ramp function on both sides. So we see that in this case, the power spectral density is not going negative. It's staying positive, even though omega is positive or negative. So this autocorrelation function can exist. And also we see that the autocorrelation function itself, that's this, is positive. It's not negative. So both the conditions are satisfied. So it's going to be an autocorrelation function. And after that, we see that if you want to see it to be a power spectral density function, if this is the function rate with just the y-axis is power spectral density, s omega, and this is omega. So it's still positive, so this can exist. Now comes the third part in which we're given a step function from minus alpha to alpha. Now in case we use it to find out the autocorrelation function, we'll first find out the Fourier transform of a step function, right? So what happens is that the Fourier transform of step function is actually a sinc function. So we see over here that the value of s omega is going negative in these regions, which cannot go. So in this case, the autocorrelation function does not exist. However, if you put in omega into the given equations, the given graph, so we simply see that the value of the power spectral density remains positive, even though alpha is negative or positive, or for that matter, omega, not alpha. Alpha is just the limits. So we see that s omega remains positive even though omega is positive, negative, or whatever. So the power spectral density can exist, but the autocorrelation function cannot exist because the Fourier transform of the autocorrelation function was turning out to be negative in some places, which is not allowed. So in this case, the autocorrelation function can exist and can't exist, and the power spectral density exists. Thank you.